Welcome guys. So I have just 1 hour today to complete the whole installation. So we are going to get started pretty soon. Just the time to recap what we did last time, where are we headed, and understanding if we are missing something or we can do better here and there. But yeah, so let's start it. Let's start. Okay. Yeah, I see no one in chat yet, so we can go ahead and start the recap. All right, so we are in the position where we have Jupyter Hub installed on a Kubernetes cluster, and we have users that can log in and register and get approved by an administrator. Then whenever the user log in, it is able to spawn a Jupyter lab where we install a lot of different packages, and one of those is MFlow and the other one is Min.io. So you have an experience like this. So you start, you log in as a user, perfect, need to log out to refresh the page, something, okay, then you log in, the request for your server start immediately, and boom, so start a container, and we will be prompt with the usual Jupyter Lab UI, with the exception that you can open notebook, terminal. As always, you have a Dask interface, so here you can launch Dask cluster that are the use case for the SOSC School on Open Science Cloud, that we are going to hold on at the beginning of December. So yeah, we include Dask. We have some particular stuff that we want to try out, that is the Jupyter AI that can help you with the AI getting information on your code. You have also an S3 bucket per user where you can log in and do whatever you want. You can store your artifacts, basically your machine learning artifacts. And then you have you are missing something though. Since this is going to be a school for open science, we thought that would be useful to have a scientific-like experiment going on. So what we miss is essentially to install on our Kubernetes cluster a dummy experiment, right? So we are going to take CYGNO experiment, dark matter experiment data and make them arise streamed through a message queue to our platform. So in this way we are evaluating and emulating how an experiment will work. So you have data arriving, you want to analyze them in batch as they arrived. So it's a very cool thing to do, and also to experiment with at the school. And yeah, so how we can do that? First of all, So first of all, we need something where to get our data, and this is not a problem from the moment because it's an external cloud service with data. Okay, and here we have our script that pulls continuously this data in. So since these data are not too much, and also we want users to get a slightly different information, avoiding to replicate the very same result for everyone. So we want this image that are actually images taken through a camera. We want this to have little bit different noise, being a bit let's say randomly adjust in order to reproduce a real scientific experiment. So you won't have the very same exact data of any other experiment. So you want to tweak a bit these images before going and put them into the message queue. Also, once we produced this image, we also want to store somewhere what you can call a Monte Carlo truth, right? You want to know if how accurate will be the forecast of the users. So you want to store somewhere the truth. So is this signal, is this background, how much, and so on and so forth. So you want to store, in other words, on a dedicated and central min.io instance. So here we have the S3 instance with MC truth. Okay. Oh, let me shut down WhatsApp. I don't even know where it is. Ah, come on. Oh, just a second. Well, I don't know. How is this freaking possible? Woo! It's not even there. Close. Well, man, I don't know. Okay, so we are to install the S3 and then a message queue and a script to load messages into the queues. Okay, this is gonna be our injection script. Okay, so we produce an injection script that download data, tweak them a bit, store a copy into an S3 bucket, and then we put the information into the queue. From the Jupyter Lab side, you only need to connect to a message queue, that is nets.io in this case, and pull all the images, all the pictures of your experiment, so getting the messages from the queue. All right, are you ready? All clear? Let's start from the object storage. Do you remember we installed already a min.io operator? And the operator, the idea was exactly this. We have a volume attached to one of our nodes. We take that and we put a tenant, a min.io tenant, on top of that. So let's take a look on how you can do this. Essentially, first of all, we need to access this volume that we attach to our machine. One efficient way that is suggested also by min.io is to take direct PEV. Driver essentially is a provider of storage that will look for your machine and look for unbound volumes. And this makes us also introducing a concept that is the kubectl plugin called Crew, that is a manager for plugins essentially. So we are on Mac at the moment, so sorry, we are on Ubuntu at the moment, so we can try this. Let's check. Let's check it out. And yeah, so we are yes, here on our node, and we are installing this plugin. Alright, cool. Now if we type kubectl crew, nothing up here. Okay, so we need this. All right, so we have crew installed. This is a package manager for kubectl plugins that allow us to install. Okay, let's do update first. Okay, and this makes us install the provider for DirectPV. Okay, so you can look at this like an additional layer that allow you to manage application that runs on Kubernetes. So we saw Helm chart, we saw kubectl apply a single manifest. Crew allow any plugin that you might find useful to do a series of application of manifests that are already built inside the software. So you have to trust, of course. So you see here are not audited by Crew, and so you need to be careful. So okay, now everything is installed. We can see DirectPV version is installed. And now, okay, no, DirectPV installed. Driver installation. We scroll down. All right, now that the operator is in place, we need to create the drivers on the nodes that are the crawlers, if you want, that are responsible to discover your volumes, right? So let's take a look and just drop this command. All right, export. We need to export the qconfig, of course, and all right, installed. And if you check the Kubernetes cluster kubectl get pod -a, you will see that now, yeah, I have a namespace called DirectPV that is installing a long series of pod that will be responsible to execute and to create the volumes that you need. So okay, while this is loading, slowly but steady, I suppose. Why we need to do this? Because now we can create a tenant. A tenant is essentially a MinIO service managed by the Kubernetes operator, and as anything managed by Kubernetes operator can be defined in a manifest with a series of custom options. The basic options that you want to use are defined here in this example. So customization, again, yet another templating for Kubernetes. Yes, we need to do something about this, right? So you can't learn so many different packages manager and yeah, and survive in any kind. But yeah, you'll get used to if you're just starting with Kubernetes. We do not have a default yet, unfortunately. You have to live with that. Okay, so everything is running, and let's see which driver we can discover. Okay, which volumes. Awesome, we have a volume mounted on Sosk Worker 1 that is usable and that has 240 gigs, right? Yeah, exactly what I did expect. So we can go ahead. We are done, right? So initialization, I don't remember if I have to initialize. I don't think so. I think the mini tenant instantiation should do all the work. So why don't we try it right away? We open a, yeah, we install the tenant command. Alright, let me just move into the injector folder to keep everything organized. And then, alright, tenant base. Now let's open tenant base.yaml. And you see that we are going to create a mini.io tenant namespace. So secret here we put everything related to min.io. So we can say Sask, and here min.io 123 is perfectly fine. We are not going to open this instance outside, so we keep everything inside our private network of the cluster. So password, storage standard, I think it should be something like this. Let's try it out. So we use only one drive because the replication of the data is already taken by the cloud provider, so we have a volume that is guaranteed to work and to be backed up, so we don't need any redundancy at this level. min.io browser, yes, why not? Okay, then console access key and console secret key. I don't think we need console secrets. We are going to use only the min.io client, so that's fine. All right, these are the metrics and the creation of the tenant. So the tenant, we call this Sask. Then opla, what happened? Come on. Sorry. Sorry about that. Sask. Then we change in 0 on. Perfect. Now this one will be Sask. Storage configuration. So bucket DNS. Okay, let's stay with that. Mount path. Right. Then we need just to understand where is the pool number of servers. Exactly, number of servers is 1. Persistent volume. Alright, so persistent volume will be 239 gigs, and the storage class should be direct PV. Volumes per server 1 again, and we are done. kubectl get storage class. This is the name of the storage class, so we need to edit it. And okay, it's not this actually, it's this. So alright, shall we try? Yeah, let's give it a try. So kubectl ctl apply -f. Okay, get pod -a. Hopefully the min.io operator now that is running here is taking care of getting the information from the min.io tenant and creating the tenant. So let's check it at our PVC if they are going to be bound. So -n min.io tenant. Okay. Pending. Let's see what's wrong. Failed to provision the volume. Requested sites. Okay. Node selector. We should select directly the node. Yeah, would be better. So node selector. Yeah. And now let's see how node selector syntax work. So Kubernetes node selector. Yeah, I'm not the kind of guy that remember everything. Not at all. So signing pod nodes, fine. Ooh, okay, node selector. Okay, easier than expected. So it should be the host name, right? Exactly. Okay, so let's try this. Get pod -a -o wide. So now this one should be assigned. Come on. Maybe it's outdated. No. Give ctr get node. Node selector. Okay, so source worker 1. Okay, let's use this one. Okay. Holy cow. Okay. Okay. Let's check again. Describe pod -n. All right. No drive found for the request topology. Node selector, this one. So what's the problem? Oh, okay, I'll try this. Delete. Get PVC. Okay. Describe. Okay, provisioning. Okay, no drive found. All right. So let's try one thing, then I think I have the solution for the current problem. So get apply. Okay. Let's see if I requested too much space. Yeah, probably is this. Okay. Okay, get part. Okay, let initialize then. Okay, install discover. Okay. Okay. Now I missed this step, right? Minus dangerous. All right, now the volumes are initializing and we are done. Good. So soon we should be okay. Provision, initializing my tenant. Good. Then get SVC in a tenant. -m. All right. So we are going to reach this Minayo server in minayo tenant .svc .cluster .local. Okay. HTTP, yes, probably. Well, maybe like this. Sounds good. HL 9000. Sorry. So now, if we go here, So it's not answering yet because no, it's running. Okay, couldn't resolve. Let's try this. Yeah, so the address is resolved, but there are network policies disallowing this kind of stuff. So let's take a look. Let's take a look to tenant base. So they are not network policy of this, but are network policy of the Jupyter app probably. Jupyter app, that is. Not here. Yeah. So you see, this is not reachable, but I suppose that this is just working fine. QCTL logs -m this. Yeah. So if I take this, yeah, not reachable. It's not reachable at all. Yeah, the console is not reachable. And this is the correct address, right? But again, from here, what the? Okay, never mind, we are going to discover this. 0 to Jupyter Hub. And anyway, the other thing that we miss is installing a nuts server. So nuts.io will be the message queue that we are going to use. So nuts.io, and together with this nuts.io, inside that we're going to install our script. So let's take a look at the script while I'm checking network policy for the Jupyter Lab, which is this is the hub, this is the proxy, single user, network tools, network policy, egress, true, DNS. Okay, one quick check will be to disable the network policy. Is not what I suggest. We need to include labels for the policy to work, because if we get pod -m j hub and we do a describe of the pod, or show labels or whatever. So dash components, yeah, and the hub instead. And the hub will be like that. Exactly. So we might need these labels here. Yeah. So let's try. So we need, first of all, inter namespace access labels. We need to put not in ignore, so in true, because I suspect that even if I tenant base and I put here in the labels these, they were labels or tenant. Enter call. Okay. They were labels, right? So okay, and I click apply. Oops. Okay. Okay. I suspect that this won't be enough for my Jupyter Lab to reach out for. Yeah. So we need to understand inter namespace label. What will be so exactly need this. We go to Jupyter App, Vim, values, network policy, true, it's possible. So let me check just the correct value here. Accept. So this is the correct value. Okay. So let's close this. We log out, we do the upgrade, and we check if the all namespace label is working. And if it's working, we are half done. Because I was mentioning before that we need a NATS.io pod that fortunately enough we can get from an image that has already been done by another tutor, that is the Landerlini. So you see, we start from the Jupyter Live image that we have, and then we create, we insert the injector script that is the one responsible to take the information, the original data from the cloud external storage, connect to the min.io, launch the NAT server, and then ensure, okay, that there are actually data locally, and then smear and compress the images, so tweaking them to make them a little bit different, logging messages, and then eventually, after picking and smearing, doing some tweak to the time of arrival and the creation of the data, so they simulate new data incoming. Once done, you simply put them into the queue, so you do nuts client publish and you're done. How you run this kind of script: you install the dependencies, numpy, nuts, your request, and whatever. You put everything inside, and then you pass the endpoint for the min.io server. That will be the one that is not working right now. Okay, so let's log in again. Okay, I think it should take some time, but it's fine. Then we get here, we get the okay, all the data coming to nuts. Let me check if this is also starting the nuts endpoint. Otherwise, we need to tweak that a bit. No, exactly. So we need also to pass a nuts server. So we bring up a nuts server through the instructions. This is probably go for the next time. We bring up a nuts server together with our pod, and then we execute this kind of script. So in this image, we are introducing all the information that we need, and we are good to go. So you see here also the image for nuts that we can use in the very same pod. So essentially, we are going to translate this Docker Compose file into a pod and use the min.io instance that we are consistently failing to reach to get all the data transformed and stored persistently. So okay, kubectl logs tenant. Okay, this is the one that we need to store. Okay, it's not working. Never mind. Let's get kubectl run -h ubuntu cool of this. Okay, image ubuntu test get pod no exec yeah, of course. Cool. Okay, the pod test, and then we do okay, almost there guys, almost there. So ubuntu test sleep infinity. Okay, kubectl exec -te ti test bash. sleep. Okay. So we are inserting this probe to understand if we manage to create the equivalent of this Docker Compose, the one with the injector, and the other one, and the other container of the pod will be a NAT server. If then we'll be able to access the min.io server that we instantiated through the min.io operator. And to do that, so I put this canary pod in here, hoping for being able to log in. Yes, apt install apt update. Come on, update apt install core. Yeah, I could have loaded BusyBox, but yeah, we are live, so no, it's not easy to get solution to this bug, but yeah, we are working it out. Alright, now we can understand if we can do it. Alright, looks good. Perfect. We are able to reach this address. We couldn't from here because the network policy doesn't allow inter-namespace networking. That is good from the perspective of security in the school, but yeah, it's not allowing us to test things quickly and efficiently. But don't worry, we're almost there. So right now, what I'm going to do is to create touch nats.yaml that essentially will have next time we resume from here. It will be very quick next time. So we are creating a pod that is similar to this one, to this Docker Compose, with the exception that here we are going to put this. Oh, come on. Okay. It was only the URL. Yes. Okay. So it will be this and 443. Then the user will be Sosk and min.io123. The origin will be this, and the NAT server will be on the localhost. So yeah, I think no, we don't need this to be network mode. Okay, we only need then service to point to NAT's port. Okay, so we bring up the services, we put it into the NAT's port, and we are good to go. Alright, we have a min.io instance. So quick recap before closing. We have a min.io instance added on top of our platform. We have a plan to create this kind of stuff. So a service that take remote images, tweak them a bit, push back into min.io servers for long-term preservation, and then on the other side put it into a message queue. Once we are there, we have everything ready. We are going to need a demo notebook just to test that all the functionalities are there, and then we are good to go. So I think we need one last episode of this series, and then I can recap all the instructions in a summary video made in an easy and shorter way. so you can digest and have better instructions together with a blog post related to this. So have a nice day, morning, evening, whatever, and thank you for joining, and stay tuned until the next episode. See you, bye bye.